So in this example problem, we're going to use Castigliano's theorem to determine the vertical deflection at point A of the cantilever beam, and we're also going to do the slope. We're also going to determine the slope at the end of the cantilever beam. So so these are going to be delta A and theta A. So we're going to use Castigliano's method to calculate delta A and theta A. So in order to do that, we know that the displacement at point A is going to be equal to du, the partial derivative of the total strain energy with respect to the force applied at point A. Okay, so so the first thing we need to know is what is our total strain energy. Okay, so if we look at our strain energy, all right, we know that's going to be equal to U of bending in this transverse, due to this transverse load, plus the U of the shear stress. In the problem statement, it told us to ignore the shear stress term, so we can set that equal to 0. Because usually it's typically very, very small. So then we're going to compare our answers versus the value of our displacement theta A in the textbook. All right. So we'll see if we end up getting the same answer. So the first thing we need to do, so we're going to now calculate U bending. Okay. So U bending, the equation for the strain energy in bending, we talked about in earlier lectures, would be equal to 1 over 2 e to the I z, and we integrate from 0 to L, and we go, be the moment would be about the z-axis would be squared dx. So the moment about the z-axis is going to be a function of x. If we take a section cut at any point, the moment required to keep the system in equilibrium, so if we sum all of our moments about the z-axis at x and we set it equal to 0, we would get mz of x, which was applied in the positive direction, plus p times x, which was our applied load. So mz of x would be equal to minus p of x. Okay, so we can plug that in to this integral here. So if we do that, we get 1 over 2 e to the I z times from 0 to L, and then we get mz, so we plug in our mz of x term, so we plug in p of x, and we'd square it. Alright, so if we do this integral, what we end up getting is we get 1 over 2 e to the I z, we integrate from 0 to L of p squared x squared dx, so it's really just the integral of x squared, so we're going to end up getting U of bending, we end up getting is going to be equal to p squared over 2e to the I z, x cubed over 3 from our length to 0. Okay, so if we get our U bending again, we'll end up getting, if we plug in from length to 0, we end up getting p squared over 6 e to the I z. When we plug in the length cubed, we end up getting, if you plug in when x is equal to L, we get L cubed, and when x is equal to 0, we get 0 cubed. So we end up getting our final answer is p squared times L cubed over 6e to the I z. Okay, so that's our first step. Alright, the second step we had, if we go back to this equation here on the top left of the page, here, is we get so the next thing we have to do is we have to take the derivative of U bending with respect to p. Alright, so we said delta A would be equal to the partial derivative of u bending with respect to our force. Alright, so our force is applied at the point. Alright, so this would be dub with respect to p. So if you look at this, we just take the derivative of this with respect to p, we would get 2p L cubed over 6e iz. Okay, so we're just taking the derivative of the p squared term here, and we're bringing it down here. Alright, so if we do all that through, we end up getting our displacement at point A is going to be equal to p L cubed over 3e to the iz. Okay, and our displacement is going to go along the direction that our force is being applied here. Right? So if we compare it to the displacement here at this point, this is equal to minus p L cubed over 3e to the I, which makes sense that our displacement should be going down or going along the negative y-axis. Okay, so our delta A should be going along the negative y direction. Okay, so all right, so that makes sense. Our value matches the solution in the back of the textbook. All right, so the second part of the problem asks us to find the slope at x is equal to 0. All right, so that one is a little bit trickier. So we know that the slope at point A is equal to the derivative of u with respect to the moment applied at point A. The issue here is that there is currently no moment being applied at point A at all in the system. So what we're going to do is we currently have our cantilever beam. Okay, we have our force being applied to it, P. Okay, and then we have our couple moment that we're going to apply to it, MA. Okay, so MA is equal to 0, but for now we're going to treat it as a variable. So we're going to say we're not going to just plug it in and be 0, and we're going to find we're going to calculate our total strain energy again. So we have our total strain energy in bending, right? So again, we're going to ignore the transverse loads. Again, it's equal to 1 over 2e to the iz, and we're going to integrate from 0 to L, and we're going to integrate mz of x squared dx. Okay, so the first thing we need to do is by taking a section cut, we can calculate what mz of x is going to be equal to. So mz of x based off of the section. So if we sum all of our moments about the z-axis at x is equal to x, what we end up getting is we get mz of x is going along the positive counterclockwise direction. We get plus p of x is going along that p times x, I should say, not p of x, is going along that counterclockwise direction, and then we get our moment is going in the negative direction or clockwise, so we're going to add that moment MA. Okay, so what we end up getting after that we do this integral is we get mz of x is going to be equal to m of a minus p of x. All right. So we can plug that into this equation here. All right, and we do that, what we end up getting is we get 1 over 2 e to the iz, integrate from 0 to L. Alright, and then we're going to plug in, we're going to square this term. So if we square this term, what we end up getting is we get MA squared minus 2ma px plus p squared x squared. Okay, and we're going to integrate that with respect to x. All right, so if we do that, we get 1 over 2e to the iz, and then if we do this integral here, what we end up getting is we get ma squared x minus ma p x squared, so the 2's canceled out here, and then we're going to get plus p cubed x squared over 3. Sorry, p squared x cubed over 3. Alright, and that's going to be go from L to 0. Okay, so if we plug in our terms for x is equal when x is equal to L and when x is equal to 0, we end up getting 1 over 2 e to the sorry about that. We get 1 over 2 e to the iz. Alright, times ma squared L minus ma p L squared plus p squared times L cubed over 3. Alright, minus ma squared times 0 minus ma p times 0 squared plus p squared over 3 times 0 cubed. Alright, those all go to 0. Alright, this whole thing ends up being 0. Alright, so we're just left with this left-hand term here. Okay, so this is our u bending. Alright, so let me just rewrite that real quick. So u bending is going to be equal to 1 over 2 e to the iz times ma squared L minus ma p L squared plus p squared L cubed over 3. Okay, then we're going to then take the derivative. So we know that the slope at that point A is going to be equal to the derivative of u bending with respect to MA. Alright, so if we do that, what we're going to end up getting is we get 1 over 2 e to the iz times ma so the derivative of ma squared times L would be equal to 2 mal. Derivative of minus ma pl squared would be equal to minus ma minus pl squared, and then the derivative of the last term would just be equal to 0 because there's no ma term. So what we end up getting is we get theta a would be equal to ma L over e to the iz minus pl squared over 2 e to the iz. Okay, at this point, all right, after we've taken the derivative with respect to ma, we will now substitute ma is equal to 0 because there is no applied load in this situation. We just need to set a dummy load in order to calculate the slope at that point. So we're going to now plug in ma is equal to 0. So what we end up getting is our true theta a is going to be equal to minus pl squared over 2e to the iz. Now, if we go to the initial problem, we are given, all right, that the slope is going to be equal to this term here. All right, so if we plug in x is equal to L, we end up getting we end up getting theta is equal to F, or P, times X, which is L, times L minus 2L, which is just equal to negative L, over 2e to the I. All right? So if we simplify that down, we end up getting P, this is just because negative L, we get minus P L squared over 2e I. All right? That is our same equation we have down here. All right, so this matches the solution in the back of the textbook. All right, so really quickly, I just want to summarize what we did here. Okay, so we first need to find the strain energy. Okay, so we found the strain energy using the strain energy equation we developed earlier in the lecture videos for bending. Okay, once we found our total strain energy due to bending, we then, to find the displacement, we took the derivative with respect to the force at that point, which was our applied force in this case. So we ended up getting the equation for the displacement at that point, and it matched the value that we had found earlier. The second thing we then did is we found the displacement, we need to find the slope at that point. So we knew that the slope had to be the partial derivative of the total bending energy with respect to the moment applied at that point. So in order to do that, we had to apply a fake moment at that same point at point A, and we then calculated our mz of x term, again, with that would be a function of ma plus our actual applied force. We plugged that into our bending moment equation, and we were able to then solve for our bending moment. We were able to solve for our strain energy due to the bending moment. Once we did that, once we found our total strain energy, we then took, due to bending, we then took the derivative with respect to that dummy moment, ma, and once we got those terms all sorted out, we then substituted in that ma would be equal to 0, ma gets canceled, and then we end up with just our minus PL squared over 2e to IZ, which again matched the solution in the back of the textbook. Okay, so this is how you can use Castigliano's method to determine either the moment at a point, or the slope at a point, or the displacement at a point for beam problems.